All right, so I hope you guys took the time to go and read this article from the American Physical Society about James Joule and his work in 1840, which, yeah, I guess that was a little while ago now. After reading this, the big takeaway for me is that he was a brewer. He brewed beer, and that's why he had access to the best thermometers that were out there. That's why he was curious about heat and energy, because he had to get that yeast at just the right temperature. That's the key. Now, before we move on from James Joule, because he is a big character sort of in the history of our understanding of science, first I want to explain a little bit about this experiment that he did here. He did many experiments, but this is one of his more famous ones, and it's probably one of the easier ones to understand, where he essentially filled a container with water, possibly another fluid, but we'll say water for now, and he put these paddle wheels in it. Now, what the paddle wheels would do would be to resist the motion. If you were to pull on it with a string, you pull it sideways, and you try to pull it with the paddle wheels, there'd be friction between the wheels and the water. Now, what he did was, by setting up a series of pulleys, he hung a mass from that. Now, what type of energy does the mass have? Yeah, exactly. Potential energy due to gravity. And if he's able to put enough mass on there that it doesn't accelerate as it falls down to the ground, so it would fall at a constant rate. What did that potential energy turn into? Don't tell me kinetic. That's right, it turned into work. And that work went into turning this pulley, which turned the paddles. Yeah. Now, where did that work go? Because if they're moving at a constant velocity, it's not changing their kinetic energy. Where did that work go? It went into thermal energy. It actually heats up the water. And if you have access to the best thermometers of the day, you can put that in there, measure the temperature, and see how the temperature changes as a function of the heat flow. All right, so James Joule, he worked with John Dalton, atomic theory, James Davies, leading chemist, and Lord Kelvin, who came up with the idea of absolute zero and the first law of thermodynamics. He had some pretty smart company there. In the problem up above, that gravity turns into kinetic energy, which turns into heat. So it's called the mechanical equivalent of heat. And remember, when we talk about gravitational potential energy and its kinetic energy, what's another name for this quantity? That's right, the total mechanical energy. So the total mechanical energy turns into heat. And what's the title of this called? Oh, yeah, the mechanical equivalent of heat. Yeah, all right. So I thought we need to do a little bit of math here. So I made up a problem. Here I've got 1,000 liters, which would be 100 kilograms of water at room temperature, 20 degrees Celsius. A 500 kilogram mass stuck on the end of this, 10 meters high. So it's a huge barrel. But have you been to a brewery? They have big things. They have huge tanks. So what I'd like you to do is to find the specific heat of water, which is equivalent to the mechanical equivalent of heat. So I can say that the gravitational energy in that hanging mass turns into heat. So potential energy due to gravity is easy, mgh. And Q, what we are going to look at is if we take a mass and the specific heat of that mass times the change in temperature, where C is the specific heat for a particular material. It's a constant for that material. It's something you look up in a chart. All right. Now, to make sure that I don't get these masses confused, that's going to be the mass of the water. This is the specific heat of the water. And let's see if we can solve for C. So if I take mgh and divide by the mass of the water times the change in temperature, and I'm going to say that now. Now, here's the thing. I went back and was looking at my notes. It's crazy how precise James Joule would have had to have been in order to get a measurement like this. And I guess that's why I mentioned in the article about the controversy of whether or not he was able to be that accurate. So going and looking at the numbers, in a 100 liters container with 500 kilograms of mass that drops 10 meters, 30 feet, the change in temperature would be really, really small. It will go from 20 degrees Celsius to 20.117 degrees Celsius. That's why we're still talking about this guy, because that is not an easy thing. Now let's take a look at the math. If we have a hanging mass of 500 kilograms times 9.8 times a height of 10 meters divided by 100 kilograms of water and a change in temperature. Let's go temperature final minus the temperature initial is equal to the specific heat of water. And do you know what we get? 4,186 joules per kilogram degree Kelvin. A step Kelvin is equal to a step in Celsius. So sometimes we'll write that as degrees Celsius. So the specific heat of water, or the mechanical equivalent of heat, when we're talking about water, is 4,186 joules. Now, what the heck? Well, let's see. Some of the experiments, one of the things that mentioned in that article was about him experimenting with electricity. If we back up just a little bit, what he's realizing is that the chemical energy supplied by a battery turns into electrical energy, which then in a resistor, as you know, what happens? The resistor gets hot. It turns into thermal energy. How could we measure that thermal energy? Well, if we had an accurate enough thermometer and we place that in a container and fill it with water, we can see how the energy goes from electrical energy into thermal energy. Things that at first glance don't seem to be equivalent. They are. You can look across the marsh. How's the nuclear power plant work? Well, we take nuclear energy, good old E equals mc squared. We split that uranium atom, a tiny bit of energy is released, into thermal energy. That thermal energy heats up the water, which turns the turbine, which produces electrical energy. That electrical energy travels through the wires, if you will, and eventually ends up at your house where it can turn into mechanical energy. Turns the fan in case you're hot, makes your toast, etc., etc. Okay, here's the thing. The idea that all of those things are equal to each other wasn't really understood before James Joule. That's his contribution. And then lastly, they always talk about this because it happened on his honeymoon. I used to make fun of him about that, and then I read the article. It turns out his wife and daughter died like 8 years later. I feel really bad. But on his honeymoon, the story was James Joule, when he went, they were visiting a waterfall, actually tried to go and measure the change in temperature of the water due to the falling down the waterfall, if you will. Because we start with gravitational potential energy, turns into kinetic energy as it falls, and then what happens at the bottom? It hits that other pool of water, gives up that kinetic energy, collides with the other molecules in the water, and would raise the temperature of the water. So that would be considered thermal energy. Yeah, James Joule. Wanted to take a minute and get to talk about that. In a moment, we'll talk a little bit more about our formulas, Q equals mc delta T, and then we'll get going on those examples.